welcome everyone. I'm so excited for today's lesson because we're doing stuff I really, really enjoy. So we're going to look at speed, velocity, and acceleration. Can a runner have an average speed and yet an average velocity of 0? That's an interesting question. The only way we can answer it is if we know the difference between speed and velocity. So, we know what vectors and scalars are. We've done frames of reference, distance, displacement. Today, we're going to look at speed, velocity, and acceleration, because those are very important, okay? So, no, that's what I wanted. There we go. What are our keywords? Speed, velocity. We normally don't have an issue with speed. It's velocity that gets us. Then we've got average speed, okay? And we've got average velocity. And we're going to look at acceleration. Some of these are new words, some of them not. We often talk about acceleration in English, and we put a whole bunch of extra words that we mean, that doesn't quite mean what science means. So we need to change some of our language here, okay? It's okay, we'll take it step by step. Here we go. So let's look at speed and velocity. First of all, we need to define these two concepts. Okay, so we're going to define what is speed, what is velocity, okay? One is a scalar, one is a vector. We've done that. Then we need to talk about what is uniform and non-uniform. This is quite important because we're going to talk about both of those. So we get uniform speed, uniform velocity, and we get non-uniform speed, non-uniform velocity. Uniform means constant. Non-uniform means not constant, so it's changing. And how velocity changes can be, it's not quite what we think. It's not just about size. Then we got average. Average speed, average velocity. And I know you're going to go, oh, but that's simple. It's average. We can do that. It is, but later on in the series, we're going to look at instantaneous. Ooh, big word. But we first got to understand what average is first, okay? So, and of course, added to all of this, once we understand what those are, we can look at our calculations, okay? We can look at our calculations. When we look at acceleration, we need to define what acceleration is. Acceleration is a vector. Acceleration is when we change the velocity of an object, okay? And then, of course, we're going to need to look at direction. Now, this is the one that's difficult because we will talk about deceleration in English. And if I told you that an object was decelerating, you'd probably tell me it's getting slower. And that's true in English. But we don't use the word decelerating in science, okay? Because it's an English word, it's a language thing. In science, we only talk about acceleration, but we have to give it a direction. And the direction of the acceleration will tell me whether an object's speeding up or slowing down. Okay, so direction, very important. Then we're going to do some calculations. So that's all very exciting, okay? And we're going to take a short break, and I will see you in a couple of minutes. Welcome back, everyone. Now, we're really going to get to the definitions of speed and velocity and all of those. But the easiest way to do that is with a little bit of a case study, okay? That's what we're going to call it. So what we have here is my friend's walk. We saw this before. And now we're going to try and make sense of it, okay? So if we look here, we've got her walk. And they say to us, now, look at what the information is at the bottom of this. Whoops, wrong way. Okay, so over here, they tell me that it took 47.50 minutes. Her average speed is 10 minutes, well, her rate. It's not actually her speed. They say it's 10 minutes, 53 seconds. So they're saying to me that my friend could walk on average a kilometer in 10 minutes and 53 seconds, okay? If I look at this and I go, let's calculate her speed. Speed is a scalar, okay? So speed needs her distance, okay? Now, let's do it on the next slide. So we knew it took 49. Let's just check. Oh, sorry, 47. I was going to make it even slower. 47. Let's just fix that. 47, oopsie. 47 minutes, okay, and 50 seconds. Now, the first thing is I can't work with minutes and seconds. I need it to only be minutes, or I need it only to be seconds, okay? So I could work this out in kilometers per minute, or kilometers per minute, per second, and speed needs to be meters per second because it works with distance, and my unit for distance is meters, and my unit for time is seconds. So I need to convert this into minutes, into seconds. So what we've got to remember is there are 60 seconds in 1 minute, okay? So here we go. I've got 47 minutes, so I'm going to take 47 times by 60. So 2,800, oh, it just sounds terrible, 2,820 seconds. So my time is 2,820 plus that 50. So my total time, 2,870 seconds. That just sounds terrible, but it's okay, it's in seconds. Her average speed, now the distance that she traveled was 4,39 kilometers. And again, we can't work in kilometers, we need to work in meters. So I have to convert my kilometers to meters, and I do that by timesing by 1,000, okay, because there's 1,000 meters in a kilometer. So I'm going to go 4.39 times by 1,000, and we get 4,390, okay? So her distance is 4,390 meters. So she went 4,390 meters in 2,870 seconds. I want her speed. So her speed is her distance divided by the time it took. So 4,390 divided by 2,870. Definitely need a calculator for this. So we've got 4,390 divided by 2,870. Has to be a decimal, so 1,53. So her average speed was 1,53 meters per second. So every second, on average, this isn't her speed at every moment, is 1,53 meters per second. That's her speed. I don't care that it went round all sorts of corners and up and down, and all, that doesn't matter. Okay, that's her average speed. The second part of this was, what is her velocity? Now, velocity requires me to use displacement. Okay. Essentially, she stopped and started at the same place. This doesn't bode well, okay? Because if I now go here and go, well, her velocity, which is a v, is going to be her change in displacement over time. Oh dear, she didn't go anywhere. So she went 0 for 2,870 seconds. She didn't do anything. This is why I don't run races, because you run all the stuff, get to the finish line, and according to science, you have no average velocity. You've gone nowhere. However, if I had to go back to this and say, what is her velocity if she ended at the 4-kilometer mark? Here I can give a velocity now, but it's still going to be very small because her velocity is only this little piece here, whatever that distance is, okay? That displacement would give me her velocity, and it would be at a certain direction. So she would be, and north is here on on this map, so she would have gone sort of southeast, southwest, but she can have a velocity. So it's possible to have an average speed, but not an average velocity. Speed doesn't rely on direction. It is a scalar. Velocity absolutely relies on direction. And velocity is about the change in position. We have to know where our starting point is. So, speed is the rate. Rate means divide by time, at which an object covers a distance. Remember, distance is a scalar. Uniform speed, which is not what the runner would have had, my walker, okay, means that the body covers, the object, not a person, covers equal distances in equal time intervals. So if I said that my friend who walked, and we said we got a speed of 1,53 meters, if she had to walk 1,53 meters per second every second for the entire motion, she has uniform speed, okay? Uniform speed isn't that difficult to achieve when we're looking at people walking or cars driving. So if we look at cars on the highway, you should go at a uniform speed of, say, 100 kilometers per hour. You can do that, okay? But it means that every hour you do 1 kilometer, okay? That's what that speed means. Average speed means it's the rate, in other words, we divide by time, at which the total distance was covered. So we calculated for my friend's walk, we calculated average speed. Basically, we ignore the times when they went really slow, and we ignore the times that they went really fast. We just look at the total distance, and we look at the total time. Average, sometimes a little bit more useful, okay? In fact, if you plan a road trip to, say, Cape Town, most people will say to you, plan it so that you'll average 60 kilometers per hour. That average means sometimes you're going to go at 120, sometimes you're going to go a little bit slower. It includes the rest stops, but it's an average. So you can plan how long it would take you to do the trip, okay? And that's if you're obeying all the laws and taking regular rests, which are important. When we look at speed, how do we calculate it? We calculate it with distance divided by time. Speed is measured in meters per second. Distance, which can also be a d, is measured in meters, okay? Time is measured in seconds. However, even though meters and seconds are our SI units, sometimes, okay, we will measure them in kilometers and hours because it makes sense to do that if we're looking at a car that's moving. Read the question, okay, as to whether they want it in meters per second or kilometers per hour. If you're not sure, meters per second, Those are the SI units, okay? If we look at average speed, now watch how my equation has changed. Average speed. I need to use total distance, total time. If I'm just calculating a speed generally and they don't tell me if it's average or not, take the distance, divide by the time they give you. If it's average speed, I need to say I'm calculating average speed. It's very, very important, okay? And I need to know that then I have to use the total distance and I have to use the total time. Be careful that you don't leave something out there. Velocity is the rate of change of position. This is the important thing. Change in position. X means horizontally. Rate of change means divide by time. We're looking at change in position, which means we have to have direction. I can't even emphasize that enough. Direction, direction, direction. And your velocity is in the same direction as your change in position. Okay? Of course, then we can have uniform velocity, which means equal changes in position over equal time periods. And here it'll sound the same. So if I say we had an average speed of 5 meters per second, or a uniform speed, I can also have a uniform velocity of 5 meters per second, but I have to tell you the direction. So I have to say I'm going north, or left, or right, okay? But I have to put a direction in it. Then we get average velocity, which means now we take total change in position divided by total time. Do you see they're very similar, speed and velocity? The difference, it's not the time that's the issue. It's whether I'm using distance or change in position. We will often say the displacement of something, that is the change in position. But we don't use the word displacement in our definitions. Definitions, very, 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 very important, okay? So, we look at our equation. Now it looks a little bit different. V is velocity measured in meters per second, same units of speed. Delta x is my change in position. Okay, measured in meters. Delta t is time, measured in seconds. Again, I could describe velocity in kilometers per hour, but we don't want to do that very often, okay? We really want to be using meters per second because that's the SI unit, okay? Then we get average. Now you've got to pay attention. Look at how I've changed my symbol. Average has to have a line on top. If you don't put the line, it doesn't mean average velocity. Again, measured in meters per second. Delta x is the same, delta t is the same, except this is total delta x, and that is total time, okay? Acceleration is the rate of change of velocity. So now I'm looking at how velocity changes over time. A is acceleration. We're going to do more of this soon, don't worry. Okay. Acceleration is meters per second squared. It's how the velocity changes in time. That is my velocity, so it's how my velocity changes. Okay, so I have to take two velocities and minus them from each other, and this is time. Okay, so when I go here, and I'm going to introduce some new symbols, it's a final velocity minus and initial velocity. Okay, you're going to see that often. But change in means the velocity has to change. Or if the velocity doesn't change, acceleration is 0. Okay, acceleration is a vector, has to have a direction. Direction's fun. Okay, so, oh look, I went and wrote over my stuff. So here we go. I put that there anyway, so VF minus VI. Oopsie, what I mean by that, final velocity, initial velocity. So I need to know two velocities, okay? Sure, lots of definitions, lots of new symbols. We're going to need to do some calculations. But that's all for now. We're going to take a short break, and I will see you in a couple of minutes. Welcome back, everyone. Now we're going to get into some calculations. So we've done all the definitions, we've looked at some concepts, now we need to put it in practice, okay? So here we have a car drives 150 kilometers in 1.5 hours. And I say calculate average speed. So what have we got? First of all, we know the distance is 150 kilometers. We know the time is 1.5 hours. Now here, because they gave my distance in kilometers and they gave me the time in hours, I'm going to calculate the speed in kilometers per hour. They don't say in meters per second, so we're going to keep it in kilometers per hour. They want average speed. So average speed, we're going to go distance divided by the time. So it's 150 divided by 1,5. Definitely need my calculator for this. Okay, so we've got 150 divided by 1.5, and I have 100. Now, I've run out of space. I should have done this better. You would do it underneath. So I get 100 kilometers, make sure it's an M, per hour, and it's to the -1. That's fine. That's his average speed. Sometimes the car may have been going faster, sometimes he may have been going slower. Average, we don't care about the middle parts. We're just saying, if I took the whole distance, what sort of speed was he going at? Okay? Now they say, what distance can a car cover if it has an average speed of 75 for 2.5 hours? Okay, so here, this isn't that it's a difficult question necessarily, but it's about writing the information you know so that you can work out which equation to use. That's usually the biggest problem is you don't know which equation to use, or you try and manipulate the equation first. Don't do that. Okay, so we want to know what distance. They say the average speed is 75 kilometers per hour, and the time it takes is 2.5 hours. Okay, so we've written the information, now we write the equation. So average speed is distance over time. I know the average speed, it's 75. I want the distance, and it's 2.5 hours. To get distance on its own, I'm going to times both sides by 2.5. So that gives me 75 times 2.5. Absolutely need my calculator. 75 times 2.5. Can't leave it as a fraction, so 187,5. And my units, kilometers. Kilometers, why? Because it was in kilometers per hour and my time was in hours. Please be careful with the units, okay? We good? Good. So, a car drives 75 kilometers while driving at 120 kilometers per hour. That should say how long does it take for the car to cover this distance? How long? Time. So what do we know? Distance, 75 kilometers. Average speed, because that's what they're telling me, okay? Or they're saying speed at, so we can just say we know what the speed is. 120 kilometers per hour, and they want to know time. So again, we've written down what we know. Now we're going to write the equation. So the equation we know is speed equals distance divided by time. He's going 75, 120 kilometers. We want time. Now this one's a little more tricky in terms of the maths, but what we're going to do is those two swap places. Okay, so in other words, time is 120 divided by 75, okay? If you can go from the second step to the answer without this middle one, do it, okay? There's no marks for showing me all the maths, but also you don't want to not show the maths and then get it wrong because you think you look silly or stupid by not showing the maths. We don't think like that, okay? We want you to get the right answer. So you do as many math steps as you need to get to the right answer, okay? As a teacher, I'd rather you get the right answer and do all the maths than try and not do all the steps and get the wrong answer because you made a mistake and you can't go back and check where the maths went wrong. Okay, so our next question. A car drives 75 kilometers while driving at 120 kilometers per hour, so that's the speed. And then this should say how long does it take for the car to cover this distance? They're asking for time. Right, what do we know? Drives 75 kilometers, distance 75. Speed 120. All right, so that's 120 kilometers per hour, and they want time. That's what I'm looking for. So now I know what I've got. I'm going to write the equation as it's given to us. So we know that speed is distance divided by time. My speed was 120. My distance is 75. Now I want time. At this point, if you can solve for t without doing all the maths, go ahead, okay? If you need to show all the math steps, show all the maths, okay? So I'm going to actually show all the maths because I think it's important. So we're going to times by t on both sides. And then I'm going to divide by 120 because the t's then cancel out on that side and the 120 cancels on that side. So t is 75 divided by 120, okay? I absolutely need my calculator for this. So 75 divided by 120, ooh, no, make sure you put it in properly because I said divided by 12 there. And I get 0.625. Remember, we round off to two decimal places, but that's exactly 3, so I'm actually going to keep all of them. What are we measuring this in? Hours, okay? Don't convert it because that looks funny. Don't convert it to minutes. Don't convert it to seconds. Hours is fine. It's a decimal. It's a fraction of an hour. which I expected because the distance was less than 120, okay? Ooh, oh, look here, now we're getting to more exciting ones. Girl pushes her toy trolley 10 meters right. She then pulls it 5 meters to the right again. That should have actually said, that's fine, we'll keep it. 7 meters to the right. Takes 10 minutes. They want her average speed and their average velocity. So she went, we need to know, we want average speed. Average speed means I need to know distance. So I want the distance, and she went 10 meters right. I don't need to put the units in here, so let's just take that out. So she went 10 meters, then she went another 5 meters, and then she went 7 meters, right? So let's add those together. 10 plus 5 plus 2, 7, 22. She went 22 meters. I'm calculating speed. Direction doesn't matter, okay? So they also tell me this takes 10 minutes. I never, ever, 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 ever work in minutes. This has to be in seconds. So to get it in seconds, I'm going to times by 60. Okay, so I'm going to take 10 minutes times by 60, gives me 600 seconds. Okay, she's not going very fast, but it's all right. She's playing with her toys. So average speed is distance over time. She went 22 meters in 600 seconds. 22 divided by 600. And I've got 0,0. We're definitely going to round this off. And I'm going to round it off to 37. So she was going 0,037 meters per second. This is a speed. I don't care about the direction at all. Doesn't matter, okay? So, oh man. Next one. Oopsie, went too far. Girl pushes trolley to the right, then pulls it again to the right, and then pushes again to 7. So now they want average velocity. Velocity means direction. So what I need is what is her displacement, okay? She pushes it to the right to start off with, so I'm going to say to the right is my positive direction. I want to change in displacement, and she changed 3 times. There's 3 displacements they give you. So she went 10 meters to the right originally, then she went another 5 meters to the right, and then she went 7. Now, if you look at this, it's actually the same value as we got for the distance. So this is 22 meters right. Okay? This is the difference, is now I have to have a direction, okay? Her time is still 10 minutes. So that means it's still 600 seconds, right? Now I need you to pay attention. How do we write this equation? They wanted average velocity. I have to use the v with the line over it. If I don't use the line over it, it doesn't mean average and the equation's wrong. That's going to be her change in displacement over her change in time. So she went 22 meters in 600 seconds. So now let me just remind you, it's still on the calculator, 22 divided by 600, which is 0,037. We're going to round it off. But we're not done. Yes, this is the same value as her average speed was. Okay, but I wanted average velocity, which means I need to give a direction. Her displacement was to the right, so her average velocity is to the right as well. Speed is a scalar, velocity is a vector. They can have the same magnitude, size, okay, but velocity is incorrect if I don't have a direction. Okay, so that brings us to the end of some simpler calculations. We're going to take a short break, and then we'll do some more calculations. So I'll see you in a couple of minutes. Welcome back, everyone. Let's dive straight into more calculations, okay? So, now we're going to do a bit of a case study with it. A car travels on a long, straight road. All right, so we've got a long, straight road, horizontal. Its velocity is recorded every second. So what you can see here is time 0, it didn't have a velocity. Then every second they're recording instantaneous velocity. Now I want you to see something. As we look at it, the first velocity, okay, that's 0. Then it's at 4 meters per second, and now it goes to 8. The difference between those two numbers is 4, okay? Then it went to 12. The difference between those two is 4. Then it went to 16. That difference is also 4. Then it went to 20. That's 4. Then it went to 24. That's 4. So if you look at it, every second, the velocity was increasing by 4 meters per second. So every second, velocity increased by 4 meters per second. So if I said what is the rate at which it's increasing by, you would go 4 meters per second divided by seconds. You know from maths, if I take that up to the top, it becomes seconds to the minus 1. So it's 4 meters per second. Oh, look at this. That's the acceleration of my car. It's accelerating at 4 meters per second squared. Every second, the acceleration is getting bigger by 4. So the velocity, is getting bigger by 4. So it's covering bigger stretches of distance in the same time period. It's getting faster, okay? What if now we go the other way around? So now look here, we have a car traveling on a straight road. Again, we record its velocity, but over here, even though time is 0, it's already moving. So the car was moving, and then as it passes a point, we start the stopwatch. So it has an initial velocity. And if you look, it's getting smaller. Let's see how much it's getting smaller by. So to go from 20 to 17, I had to minus 3. 17 to 14, we took 3 away again. 14 to 11, we took 3 away. 11 to 8, we took 3 away. 8 to 5, we took 3 away. 5 to 2, we get minus 3 again, and this would stop before the 7th second, okay? So what this is telling me is that my velocity is getting smaller by 3 meters per second every second. that means that it's 3 meters per second per second. But now we say, I'm getting a negative value here. How do we describe this? So I'm going to tell you that the car is accelerating. And right now you're all screaming at the screen going, no, it's not, Tracy, it's decelerating. Yes, in English, we would say decelerating. Not in science, okay? What it means is that there's a force acting on the car, the brakes, that's stopping it. So the acceleration is backwards. It's negative. It's getting smaller. So what we would say is this car's acceleration is 3 meters per second squared backwards. That tells me that the acceleration of my car and the velocity of my car are in opposite directions. So for the car to slow down, acceleration must be in the opposite direction, okay? Because there's a force that's stopping it from moving. Very important, okay? So negative acceleration just means it's in the opposite direction and my object will slow down. Please don't use the word decelerating. That's something we do in everyday language, but it's not actually a science word. So, cyclist starts from rest, initial velocity 0. After 7 seconds, she attains a velocity of 7 meters per second north. So, let's see what we've got. Starts from rest. Initial velocity 0. Rest, not moving. After 7 seconds, so now my time is 7 seconds, she's going 7 meters per second north. Okay? I need a direction. Now they want to acceleration. Remember, acceleration is the rate of change of velocity. So acceleration is change in velocity over change in time. Rate, I'm just going to remind you, you don't have to write it in the equation, is final minus initial. Whenever I have that delta sign, the triangle, that means change in, okay? So we take what happened last minus what happened at the beginning. It's always final minus initial. So, final, 7 minus 0 divided by 7, okay? That means 7 divided by 7. 1 meter per second squared north, because that was the direction of her velocity and she was getting faster. Now, she's traveling 12 meters per second west. So initial velocity, 12 meters per second west. She has to stop at a stop street. It takes her 10 seconds. And her final velocity is going to be 0 because she stops. They want acceleration. Oopsie. So, acceleration, change in velocity over change in time. Final velocity minus initial velocity divided by 10. So let's just check. So we've got 0 minus 12 divided by 10. I get minus 1,2. We never ever leave it as a minus. We have to change it to a positive. I, by default, made west positive. So her acceleration is 1,2 meters per second squared east. So she slows down by 1 meter per second squared, by 1 meter per second every second. Okay, she's slowing down. All right, so all right, we have done a lot. Okay, remember about the direction of acceleration. negative acceleration because it's slowing down, and the acceleration is in the opposite direction to which the object is moving at, okay? Wow, we got through a lot. I hope it's all making sense to you, but we're going to stop there for today, and I will see you again next time.